Okay, so let us continue this lesson on vectors. So when I checked the video yesterday, so I asked you a question, but we forgot to answer that. Do you remember I told you that if you have a quadrilateral that you know that two opposite sides are parallel and equal in size, we can conclude that that quadrilateral is a parallelogram. Do you remember? So, but when I checked, we forgot to talk about it later. So, why is that, by the way? So, what is your definition of a parallelogram? So, a quadrilateral is a plane shape with four sides. And then when do you say that this one is a parallelogram? Yes?
I mean, two sides are parallel and the other two sides are also parallel.
Parallel. That's the reason probably we call it parallelogram, yes? So it means that they should be pairwise parallel, the opposite sides. So, but now, so let me tell you something. So the definition of a parallelogram is this. So I have a, let me make it like this. So I have a quadrilateral ABCD, and this is, by the way, by convention you need to do it like this. You are not allowed, when you write ABCD, when you read a book and they say quadrilateral ABCD, you need to go either clockwise or anti-clockwise all the time, yes? So that's a convention. So don't write ABCD, yes? So if the picture is clear for you, that's okay. But if the picture is not clear and you are reading the text and trying to draw the figure yourself, you need to respect this rule. Okay, here, if I tell you that AB is parallel to BC and AD is parallel to BC, then you can conclude immediately based on definition of a parallelogram that this is indeed a parallelogram. But now my question is that if I tell you that AB is parallel to DC, but I don't say anything about these two being parallel or not. Instead, I tell you that and AB is equal to DC. That was the situation that we were facing yesterday, yes? We knew that these two, because you remember I told you that if vector AB is equal to vector DC, what can I conclude about vector AD and vector BC? So if AB as a vector is equal to DC as a vector, it means that they are parallel and they are equal in size. Okay, now and then I told you that therefore this is a parallelogram. So now do you think that we really can conclude that this is a parallelogram? So ABCD is a parallelogram. So now this is do you understand the question needs to be answered? So we cannot just jump over it. So this is not the definition of a parallelogram, but I'm trying to convince you, we can think together, that why if this happens, if I have a quadrilateral, so that the opposite sides are not only parallel, but equal in size, we don't need to care about if they are parallel or not. They automatically become parallel. Is the question clear? Okay, so now you need to focus using these two, show that AD has to be parallel to BC. So we need some arguments using Euclidean geometry. I just want to recall these things for you. Usually these trivial questions are hard to answer, but yes?
So I think you showed yesterday that you can like call the DC and AB X and...
You want to use vectors?
No, it's fine, just the side. We can call sides X and...
This one X?
both.
This is X.
AB and DC.
So this means this is not the segment itself. You are referring to x as the length. So you need to you need to tell me, what do you mean by x? X is the length or the segment itself? In the previous situation, I meant the length.
Yeah, sure. Yeah,
Okay.
I think it's the length now. And the y can be like the difference from C to B, like the
Yes.
x-plane.
So y is here and here, but we don't know yet they are equal.
Oh no, no, just another like variable.
No, tell me about your strategy. You don't need to give me the details.
My strategy is that if we have like the line AB and BC, like if we have them next to each other, then I mean we know from the beginning that they are equal in length.
Yes.
And they are parallel with each other. When we move it, like both points move the same amount, and like if we have them right next to each other, like they're on top of each other.
Yes.
And then we move it one unit down.
Yeah.
Then we know that. I mean, both sides.
Okay, so what you are telling me is your intuition, and that intuition is correct, but we want to refer some theorems.
Mm-hmm.
That's what I'm saying.
I just want to, like, the change in, like, we changed.
Okay, but then I can ask, how are you sure that the change would be the same? Of course, clear it is the same. This is why I want you to refer to some theorems that we already know about them. So let me give you a hint. If I myself am correct, you might want to connect point A to point C. Okay, let us see how this will go. So I will connect point A to point C. Do you think this will help? So because my goal is to show that these two are parallel. How can I achieve my goal? This is a famous thing that you need to should have in your memory. This is like a Z shape, letter Z. Whenever you are facing letter Z, this parallel and transversal should come into game, yes? So if you have, I don't know, N or Z, so do you know that if I have two parallel lines, and if I have a transversal, then I know that these two, of course these two are always equal because they are vertical angles. These two are also equal, but there is no guarantee that this is equal to this. But if they are parallel, yes, all these four are the same and all these four angles would be the same. Yes, this is the theorem. If I know they are parallel, I can conclude that. And the good point is that the converse of this theorem is also true. So if I don't know these two lines are parallel, if assume that I'm not giving you any information about this, but I am telling you this angle is equal to that angle. Yes? Then what can you conclude? That these two lines are parallel. So this is an important theorem. Yes, one of them is actually an axiom. The other can be proved using the axiom. So this is good to remember, okay? So that is what I want trying to... So by the way, you are somehow right, because this is also an axiom. So if you want to start, we didn't prove this. We accepted this as an axiom, but we were able to prove the converse. Okay, so now do you think that this will play a role here? For example, if this line is parallel to this line, and this is the transversal, I know that they are parallel. So what can I conclude? For example, I can conclude that this angle, if I call it U, this angle is also U. Yes, something I can immediately understand. Okay, but do you think that this will help me somehow? Yes, because now my goal is to prove that these two are parallel. How can I show that these two are parallel? If, let me call this angle X, let me call this angle Y. If I can show X is equal to Y, I am done. Yes? If the angle X is equal to angle Y, these two lines, I don't know yet that are they parallel or not, but I know that a third line has crossed them, and if I can show that these two angles are the same using the converse theorem, I can conclude that AD is equal to BC. Is this strategy clear? Yes or no? Dylan?
Yes.
Is it okay?
Yeah.
Okay. But do you think, how can I show that these two angles are the same? I have only this at my disposal and that. Yes?
I'm not exactly sure, but I know that the triangle ADC, they share two equal sides with the triangle ABC. They share one angle as well. And I think we can conclude that the third side is equal to the...
Yeah, you're right. What is that called? Do you remember? So Dylan is focusing on actually these two triangles. Triangle ADC and triangle ABC. Yes? Let us check. Do you agree that this blue line is a common line, is a common side between these two? Yes? And the other one, we know that AB is equal to DC. And because they are parallel, so you see I use this piece of information here. Now because they are parallel, I am using this piece of information to conclude that if this angle is U, this angle is also U. So you see I am using both pieces of information here. And now, do you remember what was the name of this? So what do you want to conclude? So let me write here. So you are saying that AB, I just want to remind you because it's geometry, it is geometry, and then we want to do with linear algebra and analytic geometry, so it is very good to remember, to refresh your memory about the geometry itself. So we know that AB is equal to DC, we know that AC is equal to AC, that's a common side, and we also know that angle U is equal to angle U here. So do you remember what can I write?
Was it angle? No.
No. Two sides and the angle between them. Side, angle, side. What can I write in front? Do you remember? They were congruent. Congruent means that you can actually put them on top of each other exactly and they will overlap. Yes? So because of two sides and the angle between them, I can conclude that the triangle ABC is congruent to the triangle ADC. And if they are congruent, then it means that this angle X is also equal to this angle Y. Yes? So this means that angle X is equal to angle Y, and then this means that because of the converse theorem, these two lines are parallel. Yes? So this means that AD is parallel to BC. Okay? And then we are done, because from the beginning I knew that these two are parallel. Now I proved that based on this extra piece of information, the other two are also parallel. Yes? And then we conclude that this is a parallelogram. So that one that I just skipped last day is because of this. Yes? It's good every now and then I will try to remind you of Euclidean geometry, by the way. That's also a very nice subject, and that is I think this is an ultimate tool for you if you want to think, yes, because you need to be very creative. Of course, not for these simple problems, but the problems of Euclidean geometry could be extremely hard. Okay. Any questions here? Okay, now let us go back to some review. So we talked about vectors, and then we introduced two operations. One operation, actually operation should be between two objects of the same set. So we learned how to multiply a negative sign by a vector. Yes? So for example, now can you tell me what can I write here? If I have a vector A and I consider negative A, and then I consider the norm of negative A, what can I write in front? What is the relation between the norm of the opposite vector with the vector itself? They are the same. So you can see algebraic, at the level of algebra, you don't need to think geometrically. So you can say that this norm sign will actually omit this negative sign. And if I ask you, so we learned also that negative of negative A is A, and then I try to convince you that even though So you shouldn't compare this because negative negative 2 is 2, so negative negative vector A is vector A. They are different, yes? I just wanted to understand that. And now let me tell you, if I give you 2 points, any 2 points, I don't know the location of these 2 points, what would be the relation between these 2 vectors? For any possible A and B, yes?
They have the same magnitude, but the direction is opposite.
So what does it mean?
One of them is multiplied by -1.
Yes, so it means that this is a rule of thumb. In vector algebra, if you interchange A and B, you should pick up a minus sign. So remember that. These rules, I think it's good to write as a remark somewhere. So for every A and B, it's very nice. If you interchange them, you have to pick up a minus sign. Yes? Is that clear? Okay. Now, what can you tell about this? Because sometimes we have to have the picture in front of us to answer. But do you think this relation is always true regardless of the positions of A, B, and C? Yes?
Well, the end point of AB and the starting point of BC is the same, so it should be true.
True, yes, because of the definition of addition, yes? But that's also a very nice rule of thumb. So if you are adding 2 vectors with their end points clear, and if these 2 points are the same, it seems that you can drop them off and write AC. So that's a very nice tool in your hand if you want to do some calculations. Okay? So here, if you want to see it, I have 3 points. There are 2 possibilities for 3 points. Either they are on the same line, yes? For example, if you really want to convince yourself that this is true, you need to consider all possible cases, yes? For example, let us consider that first, these 3 points are on the same straight line, yes? And then what happens? AB is this vector, and BC, another arrow, starts from B because it is B, then goes to C. According to the rule that we learned for vector addition, what would be AB, this arrow plus this arrow? Yes, this arrow is already started from the tip of this one, so it is exactly the form that we want. So what I need to do, if I want to add these 2 vectors, I have to start from here, okay, and then go here, and then put the tip of the arrow there. And then if I ask you what is this, you would say this is vector AC. So in this particular scenario, AB plus BC is equal to AC. But this is not all possible way. For example, it might happen that C is between A and B. Let us see in that case, does this work or not? So, for example, here is A. Let me write it in this way. For example, here is B. And let me consider that here is C. Do you think still this relation holds for this scenario? Because if I want to trust this from now on and use it as a theorem, if this is a theorem, then it means that it should survive for all possible scenarios that you can have for configuration of these 3 points. Yes? So one possibility was this: if if these 3 points are lying on the same line and B is between A and C, it was true. Yes? Now they are still lying on the same line, but this time C, I am considering C between A and B. Do you think that this is still true? It's true, yes, because AB is this vector. So let me try to convince you by drawing it a little bit here. So this is your vector AB. And now what is your vector BC? Vector BC starts from here and goes to here. So that would be vector BC, yes? Okay? And that is also a good configuration because exactly I started from the end point. And now what was the rule? I need to connect to attach these 2 points together. That would be the result vector. And where should I put the arrow? I should put the arrow on the final point, and the arrow would be here. But read this vector for me. What is this vector? This vector is exactly vector AC. So you see, it was working. What happens if they are, of course you can consider other cases yourself, but what happens if they are not on the same line? Yes, it might happen that A is here, I don't know, B is somewhere here, C is somewhere there. Yes, and this also works again, yes, because this is AB, yes, and then this is BC. And now don't look at the letters. If I give you these two arrows in this order, what would be the sum of these two? It would be a vector from the initial point to the final point, where the tip of the arrow should be on the final point. And now if I ask you read this vector, you read it AC. So this is a theorem, and that is called Shal's theorem. I think this is the way, if I remember. He was French, but pronunciation, French words are a little bit, yeah, this is the spelling, but if I remember, I checked it on the internet, so this is pronounced Shal. So this is the Shal theorem, yes? So so let me just write it formally here. No, there is an extra S, that is why it's strange. Yeah, so that the spelling was wrong. For all 3 points, A, B, and C, we have this nice relation, yes? So if I have AB, and then I have plus BC, the answer would be AC. Please remember, if you want to use this Shal's rule, you need to respect everything. This should be addition of two vectors, and the letters in between should be the same. Yes? And then that would be, then if you want to write it immediately, you can just drop these two and write AC. Okay, now let us consider some properties. So let us review some properties of addition for numbers. If I ask you addition of numbers, what are the properties that addition will enjoy for numbers? Can you tell me, name them, or if you don't remember the name, tell me what are they? For example, if I have two numbers, A and B, A plus B is exactly equal to B plus A. This is a property, yes? Of course, we take it for granted, but do not take these things for granted if you want to be a good mathematician. When you go to a new field, between new area, you need to recheck everything. Okay, so there is no guarantee that because numbers enjoy this property, commutativity, they commute, vectors also enjoy the same property. Yes? So we need to check all of them. Now, think a little bit about that. Do you think vector addition enjoys this commutativity? So does it matter if I add vector A to vector B or vector B to vector A? So let us check, yes? I have a vector A, so let us see, and then I have a vector B here. Okay, so do you remember what I told you? If I want to determine A plus B, what should I do? I should keep A the same. I have to parallel transport B here. Let me change my color. I have to parallel transport B and draw it from the tip of this. Yes, so this would be B. And then I can draw this vector. This vector that I draw is A plus B. But if I want to draw B plus A, what should I do operationally as we defined? I need to parallel transport A from the tip of here. So this would be something like that here. Yes. And then what this would be A, and then this vector would be vector B plus A. Yes? And then I need to convince myself that this blue vector here and this black vector there are equal as vectors. So it means that I have to show that they are parallel and they are of equal length and they are pointing to the same direction. But is that clear or not? Yes? I hope that you agree with me that this triangle here and that triangle there are congruent, yes? Okay, so of course you need a little bit of geometry, but geometry is so intuitively clear, so let's forgo the proof. But I hope that you agree with me that if you draw it, if you want to convince yourself, you can do it on GeoGebra with precision. So you immediately see that these two vectors would remain parallel and will be equal in size and pointing to the same direction. So A plus B, so let me write the properties. So you see the properties are very important here. So this is a theorem, so let me write theorem. Let me give it a name, properties of vector addition. Okay, so this is the theorem. I would say let A, B, and C be three vectors, B vectors. Then the first property we learned is that there is no difference between A plus B and B plus A. So this is commutativity, yes? Okay, now let us go to numbers. What is another property of addition for numbers? It's very good when you are doing math specialization, try to learn these words for those properties. So if I have three numbers, if I want to add them, do I care the order I group them? No. This is called associativity. Okay, so it means that if I have three numbers and I give you this in the exam, this is not ambiguous. So for example, if I give you in exam 2 plus 3 plus 4, you immediately answer that. Even though in principle, you should ask yourself which operation I should do first. Yes, because I have two addition operations, yes? But you are telling to yourself that it doesn't matter how I prioritize these two operations, the answer would be the same. Yeah, please try to learn these things. They are very, very important. Because then we will talk about matrices. You will see that there are some deviations from a number algebra. Okay, so you need to respect these things. Okay, I just want you to understand them deeper. So you would say that in principle, it doesn't matter here. Why? If I tell you add 2 plus 3 plus 4, you might ask me, okay, what happens if I prioritize this? Well, how should I prioritize this using symbols? Putting pair of brackets. The role of pair of brackets is to prioritize operations, yes? So here I have two addition operations, but when I write this, if you want to follow the rules, you need to show me that 2 plus 3 should be done first, and then the answer should be added to 4, so you get 9. But then, if I write 2 plus 3 plus 4, then what happens? This becomes 2 plus 7 should be written first, and of course the answer is the same. Okay, so you know that it doesn't matter which one I do first and which one second, the answer is the same. So we say that addition is associative. So it doesn't matter how you group them. Is that understandable? To make sure that you understand that, so in the exam, I can ask you this without any ambiguity. Because you say to yourself, it doesn't matter how I prioritize, the answer is 9. But I cannot ask you in the exam to calculate this. This is ambiguous. Why this is ambiguous? Because there are two divisions involved. And now let us consider them. One possibility is to consider this. Prioritize the first division. Another possibility is to prioritize the second division. Yes? But you will see the answers are not the same. So this means that this is ambiguous. I need to be careful. I cannot ask you to calculate this because I need to tell you which one I mean. But here I don't need to tell you which one I mean because the answer would be the same. It means that this operation is associative. This operation, division, is not associative. So let us check. 2 over 3 divided by 4 means multiplied by 1 over 4. And if I calculate it, it becomes 1 over 6. But if I calculate this one, it becomes 2 times 2 divided by 3 over 4. This becomes 2 times 4 over 3. And this becomes 8 over 3. And you see that they are not equal. So what we say division is not associative, but addition is associative. Which one is better if you are facing an associative operation or a non-associative one? Clearly, associative ones are easier to work with because at least we don't need to spend some of energy, some calories to draw these brackets. Yes, we don't care. But here we have, unfortunately, to prioritize. I should tell you which one I mean. So do you understand what is the meaning of associativity? And don't take these things for granted. Because your intuition always coming from numbers, if you go to more advanced mathematics, there would be a lot of deviations from real numbers. Okay, so you need to respect them. If you don't train your brain for this, then you will take everything for granted. And then all the time you will asking yourself why people are doing these. They are trivial. They are not trivial. I really want to emphasize that. Okay, now let us go back to our vectors. Do you think vector addition is also associative? And try to convince me or yourself that if it is associative, you know that if you want to show that it is associative, you need to somehow demonstrate it for me. But if you want to say that it is not associative, you need to give me an example to show that changing the priority will change the result. So for example, by this one single example, I was able to show that division is not associative. But by millions of examples, I will not be able to prove you that, look, addition is associative. Might be some people somewhere come up with an example which the results are not the same. So I have to prove it for you. But proving this is hard. It's beyond the scope of actually many. So you need to go to pure mathematics to learn what they think. And the proof of this, that this doesn't matter, comes from set theory that we started actually yesterday in Mathematics 5. Okay, so now tell me, do you think it's associative or not? Yes?
Yes, it is.
So for example, let us demonstrate it. So I need how many vectors to demonstrate it for associativity? 3 vectors. No, 2 is not enough. Because if I have 2 vectors, then I have one operation between them. Associativity comes into the game if I have more than one operation, so that I want to see that prioritizing them in different orders matter. Yes? That's the point. So I need to have 3 vectors. So for the time being, let me have this vector A. Vector B could be anywhere in this universe, but I can parallel transport it and put it from the tip of this arrow. Yes? So for example, let me assume that I have done that, and this is my vector B. And there is another vector C somewhere in this universe. I parallel transport it and try to draw this from here. But then I will have problems. Okay, where do you think I should draw that vector? There are 2 possibilities. Either the third vector coming in lies on the whiteboard, or it might happen that this is one vector, this is one vector, and assume that this is your third vector in this universe. I parallel transport it. It means that I'm not allowed to change the inclination, everything. I have to parallel transport it and put it on tip of this vector. So what happens? The third vector is not on the whiteboard. It's coming out of the whiteboard. But these are, I hope that you can convince yourself intuitively that these are 2 scenarios, not more. Either the third one also lies on this plane, or two of them lies on the plane, but the third one does not. Yes? The second one always lie on a plane. Might be it is not the whiteboard, but this is another plane. For example, I don't know, if I have this vector for A and this vector for B, if I parallel transport B here, then this hand is the plane of these two. Of course, this plane is not the whiteboard plane, but it is a plane. Yes? So it means that every two vector can form a plane for you, but the third vector might be in the same plane as the other two, or might be outside that. These are two also scenarios. Yes? Is that understandable? Okay. So now let us consider the simple case first. So for example, I parallel transported, and then this end up somewhere here. Okay. Now I ask you to tell me how to do this operationally. So now, what happens if I ask you to calculate this? Because my goal is to see that if this expression ambiguous or not. So I have two interpretations. I can say that A plus B plus C, I am prioritizing the first addition, or I might prioritize the second addition. Yes? If these two turn out to be the same, at least for this kind of cases that all three vectors lie on the same plane, this is not ambiguous. I don't need pair of brackets. Yes? Let us check. Tell me, how should I do this? How should I do that? Which one has the priority here? I have to add A to B first. Okay? And that's good because B is already drawn from the tip of A, so everything is ready. What is A plus B? A plus B is this blue vector. And if you have questions, please let me know. Do you agree? This is A plus B. And now, after this result is clear, which is the blue vector, forget about the name. I have a blue arrow. I want to add it to a black arrow C. But this is already in a good position, yes, because the second vector is being drawn from the tip of the blue vector. So everything is again ready, so I can add them. So if I add them, what will happen? I will have this vector. And if I ask you what is the name of this orange vector, you would say that I had vector A plus B, and then I add C to it. So this orange vector is the result of this. Yes? Understandable? And now let us go here. How should I do this one? The pair of brackets tell me that this has the priority. So what should I do first? I should add B to C first. So what does it mean? So I don't know, I don't have any other color, so let me just do it with black with dotted lines. Yeah? So here, do you agree? This, oops. So, yes, this is, for example, if you do it correctly, this is B plus C. Agree? Yes, understandable? So this is B, and then C comes after that. So this would be B plus C, and the arrow, this tip of the arrow should be here. Yes? And now, I am telling you that add A to this result. Now this is A. You want to add this vector to it. So what would be the result then? That would be this orange vector. So this orange vector on the one hand is this, on the other hand is this. So it means that they are the same. Okay? And then you can think, it's hard to draw it with bare hands here. So the third situation doesn't matter. Do you really think that this matters if C comes out? Try to visualize it. Everything remains the same. Yes? So A plus B would be exactly the same. But now C is coming out, so I will add this blue vector to this vector, it would be this vector. Yes? And then you can convince yourself that the second one would be exactly this vector. So now we are convinced. It's not a very rigorous mathematical proof, but it is better than nothing. Yes, the way that we started vectors geometrically, this is actually the real proof. So we are now relieved. So vector addition is associative. Yes. So what does it mean? It means that we don't need to be worried about putting pair of brackets. Yes. Now we are very, very happy because not only we can throw out the brackets, we can also commute them. So not only, so if I have a string of vectors being added together, it doesn't matter. You can take the last one and put it with the first one, add them together and add it to the third one. Whatever you want, you can do it. Yes? Okay. So number 2. So commutativity. So number 2, A plus B plus C is equal to A plus B plus C. Associativity. Okay. Of course, the other two are simple. You already know what to do. So what do you think if I add a vector to the 0 vector? Yes? What is the result here? It's the A itself. And this is also very similar to what we know from number algebra. So if someone asks you, what are you doing in class now? What is your answer? We are exploring vector algebra. Yes, so we are making a new algebra for some new kind of mathematical creatures called vectors. Yes? Okay, and then the fourth one is what? A, you already know the answer. If I add these two vectors, what would be the result? You see, this is vector A, this is vector minus A. If I add them, what will happen? It would be 0, yes? So 0 is called additive identity. And minus A is called additive inverse. Okay, it would be nice if I give you some extra pieces of information just in passing. So, do you see any deviation? Are they familiar? If I take away this vector, this symbol, what is left is just exactly like numbers. So it means that whatever we had for numbers, we also have for vector additions. And later, we will see that the same rules will apply to matrices. Okay? And they will apply in many places. So this is why mathematicians have started thinking, okay, many parts, many structures in mathematics are following very similar rules. Okay? And then mathematicians are also thinking, instead of proving one theorem several times, one in this context and one in the matrix theory, one for numbers, they give names to general structures. So we say that the set of all vectors with vector addition forms an abelian group. I just want you to know these words, okay? Because now you're being specialized in mathematics, yes? Mathematics specialization. So abelian group. Yes? So abelian Abel is the Norwegian mathematician, and here abelian means commutative. Yes? So, what can you say? You can say the set we talked about yesterday, if I have a set of all arrows in the world, all vectors in the world, together with vector addition, enjoys these four properties, and we say that vector addition and the set of all vectors form an abelian group. Okay? Let me change the language. You also know that this is true for numbers. I say that the set of all real numbers with addition of numbers forms an abelian group. Why this is good? Because if you start proving a theorem in the context of a group, you have a theorem for all groups. What does it mean? It means that whenever you see some has the same structure, you don't need to prove the theorems for that. You have already a package of theorems. You can apply them for every context. So this is the way mathematicians think. But you don't need to really, I just want you to know about these words. Okay, so far so good. Actually, even though we learned there are very big differences between numbers and vectors, but at least from memory point of view, we are relieved because everything is like as before. Yes? Is that understandable? Okay. Now, let me, when the lesson finishes, do you know? What? Pardon?
Quarter to.
Okay, so we have time. Let me ask you some questions. So let me make it short. So example, I would write simplify. Yes? For example, I just write AB plus BC plus CA. I want you to simplify that. Of course, one way is to draw a figure for yourself and understand it. Okay? But if possible, let us use Shal's theorem and these properties to master them. Yes? So, can you tell me what would be the answer? First of all, is this ambiguous, yes or no? Let me repeat everything. Is this expression you see on the board ambiguous or not? Because I am involving two addition operations. Yes?
No, it is not.
Because of?
Because of associativity.
Associativity. Yes? So it is not actually ambiguous. So what does it mean? It means that it doesn't matter in principle if I add this to this first and then add the result to this, or I add these two and add this one. Can I add this one to that one in principle? What is it, associativity or not? It's not a pure associativity. Why? Because if I intend to add this to this, I am actually commuting these two. Because I want to make this next to it. It's very important if you care about mathematics, you need to think abstractly in this way. If I want to add this one to this one, I am not just using associativity. When I want to put this next to this, it means that I am swapping these two. So if my operation is not commutative, this is not allowed. But fortunately, because this is both commutative and associative, this is allowed. Yes? So if you want. But that would be not nice. Even if it is true, it is not nice. Because here, can I use Shal's theorem? Shal's theorem, do you remember? Yes?
Yes.
Yes. Because you see that has the same structure. They have the same pattern. I have addition, A, B, and then this one starts with B, ends with another. So I can just drop them and write AC. Yes? Is that understandable? So, in principle, if you want to calculate it, method 1, you might interpret this as AB plus BC and then plus CA. And now you don't need to draw any picture to see what is the answer to this because you have Shal's theorem. What's the answer? AC. And then I have CA. Then I can solve this problem in two ways. One way is using this property. What is the relation between CA and AC? I told you that if you interchange them, it pick up a negative sign. And a vector added to its opposite becomes 0. So you know that the answer to this vector is 0. Can I use Shal's theorem again? Here. Yes?
Yes.
Yes, you can, because now I have C in common and it is lying between them. So what can I do if I want to use another Shal theorem? I drop C. What would be the result?
AA.
AA. But you know what is AA? Is 0. Okay? So you can solve it in two different ways. So method 2, let me just calculate it in different ways. So if you write this in the exam, that's okay. Or if you just immediately write 0 and convince me that they are opposite of each other. It's very important to understand AC and CA are opposite to each other. So when I add them, the answer would be 0 according to the fourth property. So now method 2, I can just prioritize the second pair. But of course, I already know that the answer would not be different, because otherwise I am in real trouble. But by the way, the only thing that mathematics cannot tolerate is inconsistency. If you find an inconsistency, it collapses actually. Yes? Okay. Yes. And the bad point is that Kurt Gödel showed that you can never ever be sure that there is no inconsistency. So we are in a limbo situation in mathematics, yes? Yeah, it's very, very deep and nice. So we can probably sometimes talk a little bit about those things. But let me see what happens here. Can I use Shal's theorem here? Yes, but this time what would be the answer? I have to copy and paste the first part. I use Shal's theorem here. What would be the answer? Just say something.
BA.
BA. And then what is the answer? Can I, let me use another Shal's theorem. Can I? Yes. So I can write again AA, but the answer is 0. So that's one place. Yes? Let me write something, another thing for you. So number 1. So number 2. So I want you to do it for me. AB plus AC. If you draw a figure, convince me using figure, that's also okay. But try to use Shal's and these properties as efficient as possible. Okay, so AB plus AC plus BC plus CA plus BA and CD. Okay, I can wait a little bit for you. And I can write one more. Okay, what's the answer to the first one? What is that?
0.
0. 0, don't say 0, the 0 vector.
The 0 vector.
Yes? So how do you go for it? What do you say?
I used the first rule, the commutativity, and
Yes.
I moved all the vectors so that I could use Shal's
Shal's,
theorem.
yeah.
Shal's.
Shal's theorem. Yes,
Shal's.
exactly. Or, yes, so exactly. So I just want you to understand, if I want to calculate it, it's very important that you go through all these steps. But can I add AB to BA immediately? They are opposite of each other, so AB and BA cancel out. But remember, When I say that AB and BA are cancelled, what I am using? I am using both commutativity and associativity. If one of them is not there, then this reasoning will fail. So, but now that we know that I can commute any pair that I like to, okay, by the way, if I do this one with this one, I am not using commutativity once, because commutativity is only between two, okay? So I am commuting these two, and then I am commuting these two, and then I am commuting these two, so that I can take this one and next to it and they cancel out. So commutativity and associativity are being used, some of them several times. Yes, this is important to understand. Yes? Okay, so now I can take AB, put it next to BA because of several commutativity and associativity. I can put AC next to CA for the same reason, and BC and CB. All of them becomes 0, so 0 plus 0 plus 0 is 0. The 0 vector. Yes? Is that understandable? So what would be here? What can I do here? What do you think? So what is the good point? If you don't want to draw, of course sometimes it is inevitable, we have to draw a picture, but otherwise, see here, I can see, for example, I can put a BE next to EA, for example. So now I am sure that I can do that, so let me write AD, and then, by the way, I can put AD next to it, and then I can use Shal theorem in one go, yes, for 3 of them. So I can write it in this way, BE, and then I would write EA, and then I would write AD. So let us take them together, and finally, and by the way, I can write CB here. Why not? Yes? But I want you to make sure it is not possible unless I know it's commutative and associative. But then you see, Shal's theorem tells me that I can get rid of this B, I can get rid of this E, I can get rid of this A. So what is left is C and D. So the answer is C, D. Yes? Understandable? Good. Now let me give you another example. This is also a good example. I just want to describe something for you here. It's simple, but I just want you to understand what is going on. Let A, B, C, D be a square. Show that this is the end. So A, C plus BD as vectors is equal to AD plus BC. Okay? So one thing becomes important. Do you remember I told you that there is a convention? When I say A, B, C, D, you have to go either clockwise or anti-clockwise. Okay? If you write A, B, C, D, then this will not hold. Okay? So I want to pause the video a little bit, let you think a little bit about that, and we can come back and solve it together. Okay. Did you come with some idea for the previous example? I added some more example here. That's also a very simple one. So, did you solve that one? Yes? Yes? So first of all, let me draw a picture for you for A, B, C, D. I have to draw a square, and I have to respect the rule that I mentioned it to you. So I draw a square. I try to draw a square, at least. And then, if I start from A, I decide to go clockwise. So this would be B, this would be C, this would be D. It doesn't matter where you start, where you're A, and if you go counterclockwise, but you need to stick to your rules. Either you go to clockwise or anti-clockwise, yes? This is a rule which is not mentioned explicitly in the question. That's a convention. Okay, now we want to show that AC, it seems a little bit strange if you want to think in terms of length, yes? It seems that this is not true, but they are not just magnitudes, they are vectors, yes? Because this tells you that vector AC, of course, AC is the diagonal of this square. Vector AC is this one. And then vector BD is this one. So what we are saying that if you add these two blue vectors, it becomes AD plus BC. Yes? So AD is this vector. And then BC is this vector. So I hope that you are not surprised, yes? Because this is an equality between vectors, not between lengths, yes? Of course, it is clear the length of this blue one is greater than the length of this orange one, the same for true. So now we are claiming that if I add these two vectors, it becomes equal to the sum of these two vectors. But equality is between two vectors, not between numbers. From number point of view, this is not correct. Is that understandable? So no surprise, yes? So how should I prove this? Do you want to say it, Dennis?
Yes, I thought of it in the way if I drew another square underneath.
Yes.
With the BD vector. So you have the AC.
So let me follow you. I don't know, that was not my idea. So let me say, you say that you make another square below it with the same size, yes? Is that what you mean?
Yes, and then I draw the BD vector from point C to the lower left-hand corner.
Yes.
Then the length from the lower corner to D is the same.
So let me name them EF. So now you can name them. What do you mean?
Yeah. So the vector AD is the same as the vector DE.
Yes.
Which is also the same as the vector BC.
Yes.
And then therefore AD plus BC.
Okay. So what you are saying is that you are starting from the right-hand side to conclude this, or the other way around. You want to go from here to here because that's an identity. You should. What is your strategy? You want to simplify this and show this is equal to this, or the other way around, or a mixture of them?
I was thinking of showing the first one.
Okay, so you are talking about AC plus BD. According to the figure that you have constructed, so what is the answer to this? Do you have any answer for here? AC plus BD. Okay. Okay. So now I understand what you are saying. Yeah, that's correct. So you are saying that I actually reflect this about this line. It becomes something completely congruent to itself. Yes. And now you are saying that AC plus BD, AC is from here to here. So you write AC, but instead of BD, you are using this idea that there is no difference between this length and that length. And of course, they are also parallel. Why they are parallel? Because this is 45 degrees and that's also 45 degrees. These are parallel, so they have to be parallel. So they are parallel, and of course, you intentionally put the arrow here, so it means that everything is... So instead of BD in your picture, I can write CE. And even I don't need to look back at the picture, because now this is Shal's rule. Who cares about the picture, yes? The answer definitely would be AE. So what you are doing the left-hand side, and you got AE. Yes?
Yeah.
But on the other hand, you can see that now we can of course continue. AE is from this vector. Yes? But this vector from A to E is A to D, D to E. Yes? Instead of AE, you write A to D plus D to E. And I don't need even to look back at the picture, because this is again the Shal's rule. AD plus DE is AE. Yes? And now ADE is this vector. What is the relation between this vector here and this vector BC? They are equal because this vector, this one is parallel to that one, the size is the same, and the direction is the same. So instead of DE, you can write what? Instead of BC. And then this means that this is the right hand side. Very good, thank you. So I wasn't thinking in that way, but this works. Yes?
Yeah, another way is to break down AC and BD in the two vectors they're made of.
Okay, so that was probably what I was thinking. So let me write another method. So let us write again with this color. The left hand side Okay, can you tell me, do you want to go from the left-hand side again?
Yeah. So.
So let me just take this away. Now this solution was finished. Now we take this away and look at another method. Okay, tell me. Instead of AC, what can I write?
AG plus GC.
AD. So let me write instead of AC, I put AD plus DC. Okay. By the way, let me give you a little bit of motivation why this is also good. First of all, I want to go from the left-hand side to the right-hand side. AC and BD, I want to take them away and bring AD and BC in. So that would be a good motivation to see if it's possible to write AC in terms of AD and BC. Of course, it was not completely done, but I was able to bring AD in at least. So there is some hope that I can solve the problem, okay? And then, instead of this, so let me put in a pair of brackets, you will probably do the same thing for BD, yes?
Yes.
So in BD, what can I write?
BC and
BC plus
CD.
CD. Of course, for BD, I can write BA plus AD, but that is not good because I have already AD that I needed, so I don't need another AD. So let us think a little bit different. So let me write it as BC plus CD. Is that understandable? Okay, and then the good point is that I want to have AD and BC next to each other. Why? Because that's the right-hand side. So I will collect them in one go because I can have commutativity and associativity. So this becomes AD plus BC collected together. And then there are two leftovers. But this leftovers is not a problem. What is DC plus CD immediately?
Yeah, the zero.
It's the zero vector because DC and CD are opposite to each other. So the sum is actually the zero vector. You can use the Shal rule. You can say DD. DD is just actually zero. And then what you get is AD plus BC, and that is the right-hand side, yes? So this method is actually more or less using, but that is also very nice. I didn't know about that method, okay? But I just want you to also learn about this and a combination of these things. Sometimes we have to add some extra line or something to picture, but sometimes we don't need. So you need to learn a combination of both of them. Yes? Okay, so let me keep this one for the next time. So the next time, the first thing that we will do is solving this problem. And I will try, because we need to proceed a little bit so that I can bring in some nice questions. And I will try to write them down, and then when we are done, I publish them immediately so that you can start working on them. But for the time being, try to solve this problem, which is very easy. But before leaving this, I just want to mention, what does this mean? This means that, what can I say about the length? You see, if AC is plus BD is AD plus BC, what can I conclude about the length? The only thing that I can conclude about the length is that the length of the total vector on the left is equal to the length of the total vector on the right. I cannot go forward anymore. You cannot say that now I can split it to the length of this plus the length of this. Do you remember yesterday we talked? The length of the sum is not usually equal to the sum of the lengths, yes? It is usually less than or smaller. Less than or equal, sorry. So the thing that I can conclude is just this. I cannot go any further. But it means that I think it's a good idea if you can draw this picture on GeoGebra and then GeoGebra tells you to parallel transport. I want you to see how you can convince yourself that this is indeed the case by GeoGebra using parallel transport. That's a good exercise to do and try to understand that. Okay, we'll stop here. Thank you. I think we have another lesson in 10 minutes here. Yes?
Yeah.
Okay.